So continuing on with Chapter 7, we're now going to discuss using what we've learned about strong, weak, and non-electrolytes to begin to write ionic and net ionic equations. So the key idea behind net ionic equations is this idea that only some of the ions in solution may participate in a chemical reaction. So for example, your total ionic equation, in a total ionic equation, we dissociate all strong electrolytes into their component ions. So for example, if we have the following chemical equation, now let's look and let's identify which of these compounds are strong electrolytes. So sodium hydroxide, is that a strong, weak, or non-electrolyte? Sodium hydroxide, is that a strong, weak, or non-electrolyte? It's a strong electrolyte, so we're going to break down sodium hydroxide into its component ions of sodium plus aqueous and OH minus aqueous. Hydrochloric acid, is that a strong, weak, or non-electrolyte? Hydrochloric acid, is that a strong, weak, or non-electrolyte? Strong, it's a strong acid, exactly right. So we break it down into its component ions. Water is not an electrolyte, so we just keep it as is. And sodium chloride being a strong electrolyte, we break it down into sodium plus and Cl minus. There we go. So this gives us what's known as the ionic equation. And from the ionic equation, we can notice something quite interesting. So looking at our ionic equation, there's a term to describe certain types of ions in our ionic equation. So spectator ions are defined as ions that do not react in a chemical reaction and do not change charge and or physical state during a chemical reaction. They're not actively participating in the chemical reaction. It's more like they're just spectating. So in a net ionic equation, the net ionic equation quite simply indicates the physical state of all ions, molecules, and compounds that participate in the chemical reaction. And the key feature of this definition is that the net ionic equation does not include spectator ions. So if we look at this equation, we notice in terms of our spectators, sodium is the same and chloride is the same both in charge and physical state in both sides of our equation. So we can cancel our spectators. And that in turn gives us the net ionic equation, which only describes the chemical species and the ions in solution that are participating in our chemical reaction. So once you have your total ionic equation, you can identify your spectator ions and then cancel your spectator ions in order to determine the net ionic equation. Does this make sense to everyone so far? Any questions so far?
So spectator ions are always just going to be like the same ones, like the repeated redundant ones?
Yes, so spectator ions will have the same physical state and charge on both sides of your reaction equation. They will not change over the course of your chemical reaction. Essentially, if the symbol, charge, and state is exactly identical, then you can cross it out. Any identical species on both sides of your reaction equation can be crossed out. Does that make sense?
Yeah.
So let's talk about the rules to write net ionic equations, and let's showcase these rules with an example. So we're given sodium chloride and silver nitrate, react to yield silver chloride and sodium nitrate. Okay. So first things first, sodium chloride is NaCl, and we know that is soluble. Silver nitrate, we have Ag plus, NO3 minus. We cross our charges. That in turn gives us AgNO3. Now, is silver nitrate soluble or insoluble? Is silver nitrate soluble or insoluble? It's a nitrate salt, so is it soluble or insoluble? Soluble, so it gets the aqueous symbol. Okay. React to yield, that tells me to draw an arrow. Silver chloride, we have silver plus and Cl minus. We cross our charges. That gives us AgCl. And what symbol do we put for silver chloride? What symbol do we put for silver chloride? Is silver chloride soluble or insoluble?
Insoluble?
Insoluble, right. So chloride salts are generally soluble except for silver, lead, and mercury. Yep, so everyone's correct in assigning the symbol of solid. Okay, sodium nitrate, so we have sodium plus and nitrate, which is NO3 minus. We cross our charges, and that gives us NaNO3. And is sodium nitrate soluble or insoluble in water? Is it soluble or insoluble? Sodium nitrate. It's a sodium salt and a nitrate salt. So it's quote unquote doubly soluble as a joke. Yeah, sodium salts and nitrate salts are always soluble in water. So now that we have the state symbols established, is this equation balanced? So is this equation balanced? Do we need to do anything to this equation to balance it? It looks balanced. Okay, perfect. So what we're going to do is we're just going to rewrite our balanced chemical equation. Always make sure you balance your chemical equation before you try to write a net ionic equation. Otherwise, you're going to be in a situation where things do not cancel properly. Okay, so now we're going to dissociate all soluble ionic compounds, strong bases, and strong acids. So sodium chloride breaks down into sodium plus and Cl minus. Silver nitrate breaks down into silver plus and nitrate, NO3 minus, aqueous. Do we dissociate silver chloride? Do we dissociate silver chloride? No, because it's insoluble, exactly right. So we keep it as a solid, and sodium nitrate we break down into sodium plus aqueous and NO3 minus aqueous. So now we have our total ionic equation. So let's just write that out one more time. And now once we have our total ionic equation, we can look and try to identify which ions are spectator ions, which ions are exactly the same before and after the chemical reaction. So, which ions are our spectator ions in this case? Which ions are exactly identical before and after the reaction in physical state and charge? Sodium, yep. And nitrate, yep. So all we have to do is cancel our spectator ions. And then we write out our remaining net ionic equation. So we have Cl minus aqueous plus silver plus aqueous leads to silver chloride solid. So this is our net ionic equation. It describes only the ions and chemical species that actually participate in a chemical reaction. Okay, any questions on this example? Let's try to apply what we've learned and let's try to visualize what's going on in a pictorial sense. So to put some pictures to this, if we've written out our equation and we've assigned our state symbols, you can draw pictures of what the solution looks like, just like we did earlier on in this chapter. And that really helps you visualize the ions present. So we have sodium plus chloride in our sodium chloride solution. We have silver plus and nitrate in our silver nitrate solution. So this will help us visualize how to break down our ionic compounds into their component ions. And then from this total ionic equation, we can in turn identify our spectator ions and cancel our spectator ions. So if you're comfortable, if you prefer drawing pictures, there's always an option available. Okay, so let's keep going now and let's talk a little bit about, and let's do another guided example. So let's look at an example where we may have to balance the chemical equation and we may have to assign some state symbols. So we have copper 2 acetate, and my question to all of you is, what state symbol do I fill in? It's a copper 2 acetate. Is that soluble or insoluble in water? Soluble, yep. So it gets the aqueous symbol. Okay. Is hydrochloric acid soluble or insoluble? Acids, are they generally water soluble or insoluble? It's soluble, yep. And one student in the chat also pointed out that it's a strong acid as well. We'll keep that in the back of our minds for later. Copper 2 chloride. It's a chloride salt. Are they generally soluble or insoluble? Copper 2 chloride. It is soluble, yep. Okay, and acetic acid, is that soluble or insoluble? Soluble, yep, exactly right. Acids in general are water soluble. Okay, so let's rewrite our chemical equation. And we may need to do a little bit of balancing. And especially for these net ionic equations, I'd really encourage you to try to balance equations by counting ions rather than focusing on individual atoms. Okay, so looking at this equation, is it balanced? Is this equation balanced as written? Is this equation balanced as written? No, it's not. So looking, we see we have 2 chlorines on the right and we have 1 chlorine on the left. So 1 times what is equal to 2? What coefficient do we need for HCl? 2, yep. Looking at copper acetate, we have 2 acetate molecules in acetic acid. We have 1 acetate ion. So 1 times what would give us 2? If we want a total of 2 acetate ion equivalents, how many acetic acid molecules do we need? 2, yep. Okay, perfect. So now that we have our balanced chemical equation, we can now begin to break down each of these soluble ionic compounds in our chemical equation into their component ions. So copper acetate. Do I dissociate copper acetate? Do I break apart copper acetate? Is it a soluble ionic compound, strong acid, or strong base? Yes, so we'll break it apart. So we have copper 2+. And then notice, since we have a subscript of 2, how many acetate ions are generated? How many acetate ions are generated looking at our subscript? 2. This is really important because this is how often things don't cancel. You need to make sure you're counting and you have the correct number of ions after dissociation. Hydrochloric acid. Do we dissociate hydrochloric acid? Is it a strong acid, soluble ionic compound, or strong base? What is hydrochloric acid? It's strong acid, so we break it apart. That gives us 2H plus because the coefficient of 2 is present, and 2Cl minus aqueous. Do we break apart copper chloride? Do we break apart copper chloride? Is it a strong acid, strong base, or soluble ionic compound? It's an ionic compound with an aqueous symbol, so we can undissociate it. That gives us copper 2+. And how many chlorides do we get? How many chlorides do we get? 2. Yep. Just be really conscientious of that. Now, my next question is, do we dissociate acetic acid? Do we dissociate acetic acid? So looking at our criteria, is acetic acid a strong acid, strong base, or soluble ionic compound? Does it fit any of those criteria? No. So then do we dissociate it? No, exactly. So we keep it together. Okay. So now we're just going to rewrite our total ionic equation. I always like to rewrite it just so that way we have some clarity in terms of what we're looking at. And so that way we can think about each aspect. Yeah, so aqueous just means it dissolves in water. But remember in our discussion of strong, weak, and non-electrolytes, for acetic acid, as it's a weak acid, the major species in solution is primarily going to be molecular compound rather than ions. We only dissociate the strong electrolytes, which are soluble ionic compounds, strong acids, and strong bases, into their component ions when thinking about net ionic equations. And that's because strong electrolytes are the only species that are completely dissociating to yield mainly ions in solution. So now that we have our equation, our total ionic equation, let's identify our spectator ions. So what are our spectator ions in this case? What are our spectator ions in this case?
The 2Cl.
Yep, chloride is exactly the same on both sides. Are there any other spectator ions?
Copper and CH3CO2.
Is that a, so looking at acetate and comparing it to acetic acid, do they have the exact same formula and physical state?
No.
Yeah, there's a small difference in that one is the anion, while the other is the protonated acid, but you're 100% correct that copper is in fact a spectator ion in this process. So now what we're going to do is we're going to take all our spectator ions and we're just going to cancel them. Noting that there should be equal numbers of spectator ion on each side. It would be a little bit odd if there were different amounts of copper on each side. That would imply that something's off with balancing this equation. So now that we've canceled our spectator ions, we're going to write out our net ionic equation. And this reaction, although it looks very complicated, essentially just boils down to the transfer of a proton from acetate to give acetic acid. So this is our net ionic equation. Does that make sense to everyone? Is everyone comfortable with this idea so far? Any questions on this example? So again, just to emphasize once again, you only dissociate your strong acids, strong bases, and soluble ionic compounds. Okay, so let's try to apply what we've learned, and let's work on the following example. And don't be shy to submit your responses via the chat or verbally. So we'll focus on trying to write out a total ionic and net ionic equation for the following reaction. Make sure to balance it first, and then we'll discuss this example in about 5 minutes. And in about 3 minutes, we're going to assign some state symbols. About 2 to 3 minutes, we'll go and assign some state symbols, just so that way everyone's on track and we're able to really practice the skills that we're looking at in this section for net ionic equations. So give your best attempt on this problem, and then don't be shy to submit your responses via the chat. The full set of Canvas review quizzes for this chapter will be posted on Canvas later today. And the proposed balanced equation that I see in the chat looks quite good. It's perfect. Hydrosulfuric acid is not on the list of strong acids that we looked at. So yes, hydrosulfuric acid would be considered a weak acid. Yep. Very good question. It's always important to consider that. And the balanced equations that I'm seeing in the chat look good so far. Let's focus on assigning state symbols, and then we'll talk about the state symbols for each of these compounds in about 1 minute. And the state symbol assignments I see in the chat look quite good. So let's discuss this example. So H2S, hydrosulfuric acid. It's a weak acid, so what state symbol do we put for acids? Are they soluble or insoluble? What state symbol do we put? Aqueous, yep. Most acids are soluble in water. So, looking at iron 3 chloride, are chloride salts generally soluble or insoluble? Soluble or insoluble? Soluble, yep. So we get the aqueous symbol. Iron 3 sulfide. Sulfide salts. Are sulfide salts generally soluble or insoluble? Sulfide salts. They're insoluble. Yeah. The way I like to remember it is the way that we actually get rid of most heavy metals in our wastewater is by generation of the sulfide or hydroxide salt. With that aside, hydrochloric acid, is that soluble or insoluble in water? Is hydrochloric acid soluble or insoluble? It's soluble, okay? Now, while we're here, let's do a balancing exercise, because if you don't have a balanced equation, you're sort of stuck with regards to writing a net ionic equation. So we have 2 irons on the right. We have 1 iron on the left. 1 times what would give us 2? 1 times what would give us 2? 2, yep. Okay. So now we have 3 chlorine times 2, which gives us 6 chlorines. And if we have 1 hydrogen and 1 chlorine on the left, 1 times what would give us 6? 1 times what would give us 6? 6, exactly. Okay. So now we have 3 sulfurs on the right. We have 2 hydrogens and 1 sulfur on the left. 1 times what would give us 3 sulfur and 6 hydrogen? 1 times what would give us 3? What coefficient do we need for hydrosulfuric acid? 3. Okay, so now we'll write out, whoops, that's not the right color. So now let's write out our balanced chemical equation. And now I'd like you to take a few moments and try to write out the total ionic and net ionic equation. And don't be shy to message me your proposed response for the total ionic and net ionic equation in the chat. And we'll discuss this example in about 3 minutes. And if you have any questions, don't be shy to ask them via Canvas, or unmute and ask your questions verbally, or type your questions in the chat as a public or private message. So let's keep working through this problem and then we'll discuss momentarily. And we'll discuss this example in another 2 minutes. And I'd like to see just a few responses in the chat, or at least any questions that you have in the chat. Really, when you're working through these problems, if there's any question that pops up, don't be shy to write it down or ask it, because often when you're working through a problem, the same kinds of questions you have at your first pass through a problem are the same types of questions that you'd have when you're looking at this problem on an exam or something similar to that. And we'll discuss in another minute to minute and a half.
Hey, Professor.
Yes. Mm-hmm.
Back to that acetic acid.
Yes.
A weak acid, which makes it a weak electrolyte, right?
Yes. Yes. And
So
yes.
Go ahead.
And because they're weak acids, we have mainly molecules in solution, so we don't dissociate weak acids.
Okay, so then that's going to be the case for the hydrosulfuric that we have?
Yes, exactly right. It's weak, so we don't dissociate it. That's exactly correct.
But on the hydrochloric, on the product side, we do turn that into its ions because
Yes.
it's a strong acid?
Yep, exactly right. Mm-hmm. And
Okay.
that's part of why we really focused on what makes a strong acid, what makes a weak acid. It comes up a lot when thinking about net ionic equations.
Okay,
Yep.
thank you.
Mm-hmm. And the responses I'm seeing in the chat so far look good, and we'll discuss in about another 30 seconds. Okay, so let's discuss this example. So first and foremost, as we've alluded to in our discussion, hydrosulfuric acid is a weak acid, and we do not dissociate weak acids and bases. Even though they generate a small amount of ions in solution, for the purposes of net ionic equations, we see mainly molecules in solution. Looking at iron 3 chloride, do we dissociate iron 3 chloride? Is iron 3 chloride a soluble ionic compound? Is iron 3 chloride a soluble ionic compound? Yes, so that gives us 2 iron 3 plus. Remember, you have to take into account your coefficient and your subscript. 2 times 1 is 2. And for chloride, how many chloride ions are generated from iron 3 chloride? 2 times 3 gives us how many chlorides in solution? 6. Always make sure to be meticulous with your counting. A lot of chemistry can be boiled down to counting things very carefully. So thinking about iron 3 sulfide, as it's an insoluble compound, do we dissociate it? Do we dissociate it? Do we dissociate iron 3 sulfide? No, so we leave it with a solid symbol. And then finally, hydrochloric acid, as it's a strong acid, do we dissociate hydrochloric acid? Do we dissociate hydrochloric acid? Yes, so that breaks down into 6H plus aqueous plus 6Cl minus aqueous. So this is our total ionic equation. So now I'm going to rewrite our total ionic equation. And the reason why I'm rewriting it is because we're going to cancel off our spectators. And I just want to make it so once I do that, it's very easy for me to just write out my net ionic equation and not have to worry about it. Okay, so now that we have our total ionic equation, Which ions are spectator ions? Which ions are spectator ions? Chloride, yep. So let's cancel chloride. Are there any other spectator ions? Doesn't look like it. So this gives us the following net ionic equation, where we have 3H2S aqueous plus 2 iron 3 plus aqueous leads to iron 3 sulfide solid plus 6H plus aqueous. So iron 3 plus is known, can be classified as what's known as a Lewis acid. So you often see sometimes people say some metals are acidic in water. And the way that that works is that the metal is reacting with weak acids in solution to generate a precipitate and a very strong acid, H+. So that's why iron 3+ is quote unquote can generate quote unquote acidic solutions. Does this example make sense to everyone? Any questions on writing net ionic equations? This is something you'll be using in both semesters of general chemistry a lot. Okay, so with this established, let's work on developing this skill via practice. Practice makes perfect on these sorts of problems. So I'd like you to take a look at the following chemical equation. And as you notice, when we go through each of these examples, we noticed we are doing essentially a survey of all the different types of reactions that you're going to encounter throughout this class and in future chemistry classes. So let's spend about 2 minutes making sure that we get a balanced chemical equation and that we have our state symbols assigned. And then we'll discuss the first part of this question in about 2 to 3 minutes. And you may need to have your solubility table out and ready to go. And if there are any questions working through this example, don't be shy to ask. Not necessarily. So metals that are by themselves, as when we discussed about the formula for pure elements, most pure elements are insoluble in water, and you just put the state symbol of that element at room temperature. So for example, iron is a metal and it's naturally a solid at room temperature, and it's not going to dissolve in water, so you're going to put the solid state symbol. And that's true for all metals. 1A and 2A cations, the ions are soluble, and ionic compounds containing 1A and 2A metals are generally soluble, but the pure element is typically not soluble in water. Does that make sense? Did that address your question? Perfect. So the state symbols I'm seeing so far look good. Let's spend about another minute to minute and a half on this example, making sure our state symbols are assigned and this equation is balanced properly. And if something ever goes wrong when you're trying to set up these equations, just always check, is my equation balanced? And the balanced coefficients that I'm seeing in the chat look quite good. Okay, so let's discuss. So what state symbol should we assign for calcium? I always like to think about it intuitively. If I have a piece of metal like steel or iron, it's not going to dissolve in water. So what state symbol do we put for a pure metal? What state symbol do we put for a pure metal? Solid. Yep. Iron 3 sulfate. What state symbol do we put for iron 3 sulfate? In general, most sulfate salts, are they soluble or insoluble? Most sulfate salts are soluble. Yeah. Okay, calcium sulfate. If we look at our solubility table in the sulfate solubility rules, I'd like you to tell me, is calcium an exception? Is calcium an exception? Is it soluble or is it insoluble? It's an exception. It's insoluble. So we put a solid symbol. And then iron. What state symbol do we put for iron? As it's a pure element and it's a pure metal, what state symbol do we put? Solid. Yep. Okay. Perfect. So now we have our state symbols established. Now let's do some quick atom counting. So we have 2 irons and 3 sulfates on the left. We have 1 sulfate on the right and 1 iron on the right. So let's start with iron. 1 times what would give us 2 irons? 1 times what would give us 2? 2. We have 1 sulfate. 1 times what would give us 3? How many calcium sulfates do we need? 3. Okay, unfortunately, we also ended up generating 3 calciums. So then 1 calcium times what would give us 3 calciums? 1 times what would give us 3? One times what would give us 3? 3. Okay, perfect. So now that we have this equation set up, I'd like you to take about 2 minutes in order to write out the total ionic and net ionic equation for the following reaction. And don't be shy to message your proposed net ionic equation or total ionic equation in the chat. And in response to the equation that I see in the chat, my one comment would be is you to make sure that you're only canceling atoms and ions with the exact same physical state and charge. Does that make sense? Make sure you're only canceling species with the same physical state and the same charge. And we'll discuss this example in about another minute. Okay, so let's discuss this example. There may be cases where nothing cancels out. And that's an important principle of net ionic and total ionic equations. Sometimes the net ionic and the total ionic equations are identical. So let's showcase that. So calcium has a solid symbol, so we're obviously not dissociating that. Do we dissociate iron 3 sulfate? Do we dissociate iron 3 sulfate? Do we dissociate iron 3 sulfate? It's soluble, so we dissociate it. And the reason why I like to balance by counting ions is it lets me very quickly shortcut and just write out the number of each ion and the charge that I spent a lot of effort generating earlier. It's always important to think about ways to improve efficiency. Okay, calcium sulfate. Do we dissociate calcium sulfate? We do not. It has a solid symbol, exactly right. So that gives us calcium sulfate, solid, and iron is a brick. It's not soluble in water. Okay, now this question is explicitly designed to test one principle. So looking at this equation, one moment. So looking at this equation, are there any spectator ions? Are there any spectator ions? No. So you may think, oh, these irons look similar. Well, the two iron atoms have a different physical state and a different charge, so you do not cancel them. So here we have our total ionic equation, and our net ionic equation is identical to our total ionic equation. So sometimes you don't actually have to do a lot of canceling, which is good. As long as you're following the rules for writing out net ionic equations and respecting the solubility rules, you shouldn't have any issues working through most of the chemical reactions that we see in this class. So, any questions on this example, or do we want to practice another example? Let's practice another example. So let's look at the following problem. Let's assign state symbols and balance this chemical equation. And then once we balance the chemical equation, we'll then write a total ionic and net ionic equation. So we'll spend about 2 to 3 minutes balancing the equation and setting up our state symbols. And then we'll discuss the first part of this question in about 2 to 3 minutes. And again, don't be shy to message your proposed responses in the chat. Or if you have any questions, don't be shy to unmute and ask your question verbally or submit your questions in the chat. And the balance coefficients I see in the chat look quite good so far. And the state symbols I see submitted in the chat look great so far. And we'll discuss the first part of this example in about another minute to a minute and a half. So let's discuss this example now. So copper hydroxide, hydroxide salts, are they generally soluble or insoluble in water? Hydroxide salts, are they generally soluble or insoluble in water? Hydroxides, soluble or insoluble? Insoluble, so we put a solid symbol. Hydrobromic acid. Acids, are they typically soluble or insoluble in water? Acids, are they soluble or insoluble? Soluble, so they get an aqueous symbol. Copper to bromide. So bromide salts, are they generally soluble or insoluble? Soluble, yep. Bromides in generally are soluble, barring a few exceptions. Water, we just put a liquid symbol. Okay, now let's do some balancing. So looking at this left side, we have 1 bromine and 1 hydrogen. And if we want to get 2 bromines, what state symbol do we need per hydrobromic acid? What coefficient do we need for hydrobromic acid? 1 times what would give us 2? So we need a coefficient of 2. Okay. So adding up our hydrogens, that in turn gives us 4 hydrogens on the left. So if we have 2 hydrogens on the right, 2 times what would give us 4? 2 times what would give us 4? What coefficient do we need for water? 2. Okay, so now that we have our balanced equation established, let's take about 2 minutes in order to write out our total ionic and net ionic equation. And don't be shy to message your proposed total ionic and net ionic equation in the chat. And we'll discuss in about 2 minutes. And the balanced equation I'm seeing in the chat looks good so far. And the net ionic equation I see in the chat also looks great so far. So let's discuss this example now, and let's talk through each of the components. So copper hydroxide, as it's insoluble, do we dissociate copper hydroxide? Do we dissociate copper hydroxide? No, so that gives us copper hydroxide, solid. Do we dissociate hydrobromic acid? Do we dissociate hydrobromic acid? Yep, so that gives us 2H plus aqueous plus 2 Br minus aqueous. Okay. Do we dissociate copper bromide? Yes, it's soluble. So we break copper 2 bromide into copper 2 plus and 2 bromide ions. Okay, and then water, we keep exactly as is, 2H2O liquid. We don't dissociate pure solids and liquids. So now what we're going to do is we're going to identify our spectator ions. And what are our spectator ions in this case? What are our spectator ions in this case? Which ions are identical in physical state and charge? Bromide, yep. So now we just write out our remaining ions to give our net ionic equation. Well, remaining ions and molecular species. Here we go. So we have the following net ionic equation. Any questions on this example? Any questions on this example? Okay, so let's do another example to continue practicing this idea of net ionic equations. So let's take a look at the following reaction and let's try to write a net ionic equation for this reaction as well as a total ionic equation. So we'll discuss the state symbol assignment and the balanced chemical equation in about 2 to 3 minutes. And the balanced coefficients I see in the chat look good so far. Let's spend a few minutes and then we'll discuss the balanced chemical equation as well as the state symbols in about another minute and a half. And the proposed state symbols I see in the chat look great so far. Let's keep working through balancing the equation and assigning our state symbols, and we'll discuss in about another minute the first half of this question. And if there are any questions, sure. If you have a proposed solution, you're welcome to write. Yep, that's more than okay. So let's discuss our state symbol assignments and let's assign state symbols. So aluminum, which is a pure element, what state symbol do we put for aluminum? What state symbol do we put for aluminum? Solid, yep. Zinc sulfate. Are sulfate salts generally soluble or insoluble? Is zinc sulfate soluble or insoluble? It's soluble, so we'd assign the aqueous symbol. And then aluminum sulfate, again, are sulfate salts generally soluble or insoluble? Soluble, yep. So we'd put the aqueous, oh, whoops. Let me just clear that just for right now, just so that way when I transfer this over and I export, we're able to see it when I export it into the shared class note set. And then zinc, is zinc the pure element, soluble or insoluble? What symbol do we put for the pure element zinc? Solid, yep. Perfect. So now we have to balance this chemical equation. We have one aluminum on the left, we have two aluminums on the right. Okay. So then 1 times what would give us 3 aluminums? 1 times what would give us 3? 3, yeah. And then for aluminum sulfate, we also see we have 3 sulfate ions. And for zinc sulfate, we have 1 zinc and then 1 sulfate. So 1 times what would give us 3 sulfates? What coefficient do we need for zinc sulfate? 3, exactly right. And then for zinc, if we now have 3 zinc atoms, 1 times what would give us 3 zinc atoms? 1 times what? 3, yep. So now that we have the following balanced equation, let's take about, oh, sorry, there's 2 aluminums. Let me correct that. So we need a coefficient of 2 here. Okay, so now that we have the balanced chemical equation, let's take about another 2 to 3 minutes and let's try to write out the net and total ionic equation. And for those who are using the annotate feature, you're more than welcome to write your proposed total and net ionic equation into the sections below. And looking at the proposed net ionic equation that I see in the chat, it looks reasonable, but make sure to put in the charges. And the proposed total ionic equation that I'm seeing in the chat looks great so far. Let's keep working on this example and we'll discuss in about another minute and a half. Yep, and the total ionic equation that I see drawn looks perfect. Let's try to get a proposed net ionic. In fact, the student who's drawing is already writing out the net ionic equation. This is quite good. Yep, and that net ionic equation looks perfect. So let's discuss this example now. I'm just going to clear just so that way when I rewrite the solution, it's visible when I export this file. So let's look at our total. So aluminum, we do not dissociate because it's a pure element. Zinc sulfate breaks down into 3, zinc 2+ aqueous, and 3 sulfate aqueous. Aluminum sulfate breaks down into 2 aluminum 3+ aqueous and 3 sulfate aqueous. And zinc we keep exactly the same, and we have 3, whoops, let me make that a little easier to see. We have 3 zinc atoms. Now we have identified that sulfate is our spectator. We can't cancel aluminum or zinc because the charge and physical state are different. So for our net ionic equation, we get 2 aluminum plus 3 zinc 2+. leads to 2 aluminum 3+ aqueous plus 3 zinc solid. So here is our net ionic equation. And this example was done perfectly by the class. The responses I see in the chat and via the annotate feature were quite good. Let's do another example. This time I'm going to show you how we would deal with writing a net ionic equation from a word statement. Okay? So I'll be doing the guided example for this example. So sodium carbonate. So we have sodium plus CO3 2-. We cross our charges. That in turn gives us Na2CO3. We'll worry about the state symbols a little bit later in this discussion. Silver nitrate, we have silver plus and NO3-. We cross our charges. That in turn gives us AgNO3. Mixed to yield, that means I have to draw an arrow. Sodium nitrate, NaNO3. So we have sodium plus NO3-. We cross our charges. That gives us NaNO3. And then finally, silver carbonate. We have silver plus CO3 2-. We cross our charges. And that in turn gives us Ag2CO3. Now let's assign some state symbols. Sodium carbonate, a sodium salt. Is that soluble or insoluble? Sodium carbonate, which is a sodium salt. Soluble, exactly right. Silver nitrate, which is a nitrate salt. Is that soluble or insoluble? Nitrate salts, are they soluble or insoluble? And don't be shy to share your responses in the chat or verbally. Yep, it's soluble. It gets the aqueous symbol. Sodium nitrate, it's a sodium salt and a nitrate salt, so it gets the aqueous symbol. Silver carbonate, are carbonate salts in general soluble or insoluble? Insoluble, so it gets a solid symbol. Okay, so now we have to check that this equation is balanced. So as we notice, we have one, whoops, that's not the correct pen color. We have one silver on the left, and we have 2 silvers on the right. So 1 times what would give us 2 silvers? What coefficient do we need for silver nitrate? 2, yep. We also know that we have 1 sodium on the right and we have 2 sodiums on the left. So 1 times what would give us 2 sodium atoms? Again, a coefficient of 2. Now, for our ionic equation, we're going to dissociate each of our soluble ionic compounds. So sodium carbonate gets dissociated into 2 sodium plus and carbonate CO3 2-. Silver nitrate, do we dissociate silver nitrate? Do we dissociate silver nitrate into its component ions? Do we dissociate silver nitrate? Yes, so we get 2 silver plus aqueous plus 2 NO3- aqueous. Sodium nitrate, we also dissociate into 2 sodium plus aqueous plus 2, oops, one moment. One second, allow me one moment just to reset OneNote. Okay, so continuing on, so we dissociated all of our soluble ionic compounds, strong acids, and strong bases. Okay, so we have our ionic equation written out. And now what we have to do is we have to cancel our spectator ions. And what are our spectator ions in this case? What ions are identical on both sides of our reaction equation? Which ions are identical on both sides of our reaction equation? What are the spectator ions? Sodium, yep. Are there any other spectator ions? Are there any other spectator ions? Nitrate. Good. Okay, so now we just write out our remaining ions as part of our net ionic equation. So we have CO3 2 minus aqueous plus 2 silver plus aqueous leads to silver carbonate solid. Perfect. So the only thing that's new when you're writing out a net ionic equation from a word equation is that you have to be very careful to ensure that your formulas written are correct. So you have to refresh your nomenclature skills in order to be comfortable with writing out the formulas from the name. Any questions on this example? Any questions on this example? If not, let's keep going and let's have you work on the following example. I'd like you to write a balanced chemical equation with the proper state symbols for the following reaction. And then I'd like you to write a total ionic and net ionic equation. So we'll discuss the balanced equation with the correct state symbols in about 3 minutes. And don't be shy to submit your responses via the chat. And don't be shy to message. Oh, we're already seeing a proposed solution drawn out using the annotate feature. And it's looking good so far. The formulas and state symbols look reasonable. Let's keep working through this problem and we'll discuss in about another minute and a half. And the equation I see drawn out using the annotate feature looks quite good. So let's discuss this example and let's rewrite and go over the instructor solution. But the response I see in the annotate feature is 100% correct. With one point that we're going to discuss when we go through this example. So let's discuss now and let's talk a little bit about the following example. So barium chloride, barium is barium 2+, chloride is Cl-. We cross the charges, that gives us barium chloride, aqueous. Copper 2 sulfate, copper 2+, SO4 2-. We cross the charges, that gives us CuSO4, and copper sulfate is soluble. Okay, barium sulfate, so we have barium 2+, SO4 2-. We cross the charges, that gives us BaSO4. And my question to all of you is, what is the state symbol for barium sulfate? Is it soluble or insoluble? Is barium sulfate soluble or insoluble? Barium sulfate soluble or insoluble? It's insoluble, so it gets a solid symbol. And then copper 2 chloride, we have copper 2+ and Cl-. We cross our charges. That gives us CuCl2, aqueous. So now that we have our equation and we take a look at it momentarily and we notice that it is in fact balanced, I'd like you to take the next step and I'd like you to try to write out the ionic and net ionic equation. And we'll discuss this example in about 2 minutes. And the proposed total ionic equation looks great so far in the annotate feature. And the proposed net ionic equation that I see in the chat looks perfect so far. So considering the class's pool of responses and the fact that everything looks quite good so far, let's now discuss this example and let's draw the instructor solution. But the responses I see look perfect. So first things first, barium chloride is soluble. So we dissociate barium chloride into barium 2+ and 2Cl- aqueous. Copper sulfate is soluble. So we dissociate it into copper 2+ and SO4 2-. Barium sulfate is insoluble. So we keep it as a solid ionic compound. And copper chloride is soluble. So we break it down into copper 2+ and 2Cl- aqueous. Then to write out our net ionic equation, we cancel our spectators of copper and chloride. And that in turn gives us a net ionic equation of barium 2+ aqueous plus SO4 2- aqueous leads to barium sulfate solid. Perfect. And the responses I see in the chat and shared via the annotate feature from students were perfect. Okay, so let's keep going with this chapter and let's do one more example. So again, we're solving a word problem and we're given a solution of potassium hydroxide and iron 2 nitrate are mixed to give potassium nitrate and iron 2 hydroxide. So I'd like you to write out the chemical equation and balance the chemical equation with the correct state symbols. And we'll discuss that first part of this question in about 2 to 3 minutes. And the equation that I see written using the annotate feature looks quite good so far. And the state symbols look perfect. The only thing that's missing is the balanced coefficients, but everything else looks perfect. Let's spend about another minute on this problem and then we'll discuss the balanced equation with state symbols. So the student proposed solutions look perfect. So allow me to write out the balanced equation and provide the state symbols. So potassium hydroxide, we have potassium plus and hydroxide. We cross our charges, that gives us KOH aqueous. Iron 2 nitrate, so we have iron 2 plus, NO3 minus. We cross our charges, that in turn gives us Fe NO3 2 aqueous. Again, because it's a nitrate salt. Potassium nitrate is KNO3. So K plus NO3 minus, we cross our charges, that gives us KNO3. And then iron 2 hydroxide, we have Fe2 plus, OH minus. We cross our charges, that gives us FeOH2. And iron 2 hydroxide. Our hydroxide salts generally soluble or insoluble. Our hydroxide salts generally soluble or insoluble. Insoluble, so they get a solid symbol. Now checking our equation. we notice in terms of ion counting, we have 2 hydroxides on the right. We have 1 hydroxide on the left. 1 times what gives us 2? 1 times what would give us 2? What coefficient do we need for potassium hydroxide? 2. For nitrate, we have 2 nitrates on the left. We have 1 nitrate on the right. So 1 times 2 would give us the 2 nitrates that we need. So here we go. Here's our balanced chemical equation. Let's take about another 2 to 3 minutes and try to write out an ionic and net ionic equation. And we'll discuss this example in about 2 to 3 minutes. And the proposed total ionic equation that I see looks perfect so far. And don't be shy to message your proposed responses in the chat. Just keep in mind that iron hydroxide is insoluble. So you can only dissociate soluble ionic compounds, strong acids, and strong bases. Yep, so the total ionic and net ionic equation that I see proposed via the annotate feature looks perfect. So allow me to clear it, and then we'll write out our instructor solution just so that way in the notes it's visible. So in terms of the ionic equation, we break up potassium hydroxide into potassium plus and OH minus aqueous. Iron 2 nitrate gets broken up into iron 2 plus aqueous and 2 nitrate ions. Potassium nitrate gets broken up into 2 potassium plus and 2 nitrate ions. And iron 2 hydroxide we keep together because it's insoluble. Now we cancel our spectator ions, which are potassium and nitrate, and that in turn gives us as our net ionic equation, iron 2 plus aqueous plus 2 OH minus aqueous leads to iron 2 hydroxide solid. Any questions on this example? So let's keep going and let's now talk about a major subclass of reaction. And in this chapter, we're going to review different types of reactions and talk about how to predict the products from each of these reactions. So the first major type of reaction that we're going to look at is known as a precipitation reaction. We've actually already seen a lot of these reactions both in lecture and in laboratory. So in a precipitation reaction, we are mixing solutions of soluble ionic compounds to generate an insoluble ionic compound known as a precipitate. So anytime you see formation of an insoluble ionic compound from 2 solutions, I'd want you to think precipitation reaction. Now, An interesting thing about precipitation reactions is that the net ionic equation for a precipitation reaction is generally the reaction of the cation and anion to yield a precipitate. Not always, but most of the time. So for example, if we look at the following equation, breaking apart all of our soluble ionic compounds, we get the following total ionic equation. And as you notice, our total ionic equation simplifies after we cancel out our spectators. Our total ionic equation simplifies to the combination of our cation and anion to form our precipitate. So we have barium 2 plus SO4 2 minus leads to barium sulfate solid. So this is just one thing to keep in mind. It helps you partially check your work when you're writing net ionic equations for precipitation reactions. So it's nice that we're able to write the net ionic equation for a precipitation reaction, and precipitation reactions are pretty easy to identify. They make a solid. They generate an insoluble ionic compound. That's nice. Now what we're going to do is we're going to talk about how to predict precipitation reactions. And we're going to use some pictures to help us visualize what's going on. So suppose we mix potassium iodide and lead nitrate. And we're asked to figure out, what do we get from this reaction? Well, the first step is to take all of your soluble ionic compounds, and you're going to dissociate all of your soluble ionic compounds, strong acids, and strong bases. We need to see what ions are present in solution in order to predict what products will be generated. So for example, potassium iodide can be broken up into potassium plus aqueous and I minus aqueous. Lead nitrate, let me write this out a little more clearly. So lead nitrate can be broken down into lead 2 plus and 2 nitrate ions. So now that we have all of our ions established in solution, we're going to play a bit of a game where we pair each cation with each anion, and we're going to write a list of all possible ionic compounds. Okay. So looking at the following pool of ions, I like to make a little list. So in terms of my cations, I have potassium plus and lead 2 plus. In terms of my anions, I have nitrate and iodide. So then what I'm going to do is I'm going to create a list of possible compounds. So the first, I'm going to cross potassium and nitrate to give me KNO3. That's soluble, so we haven't really gotten anywhere here. Then we have lead 2 plus and I minus. We cross our charges. That gives us lead iodide. And lead iodide is insoluble, so I'm going to put a circle around it. That insoluble compound will be our precipitate. Okay. So then, if a precipitate forms, we're going to write that out as our product. So we have potassium iodide aqueous plus lead nitrate aqueous leads to lead iodide solid. That's our precipitate. And then as a byproduct, we get potassium nitrate. Another way to think about precipitation reactions is that you essentially swap your cations and write a formula that is correct for the cation charge. Now, looking at this equation, is this equation currently balanced? Is this equation currently balanced? No, it's not. So looking, we have 2 iodides on the right. We have 1 iodide on the left. So we need a coefficient of 2 in front of potassium iodide and a coefficient of 2 in front of potassium nitrate. So there we go. Now our equation's balanced. And if you're curious about what the net ionic equation would look like, it would boil down to lead 2+ aqueous plus 2I- aqueous leads to lead iodide solid. The reason why I like this ion pairing method is it makes it very easy to figure out what your net ionic equation is. Does this idea make sense to everyone? Is everyone comfortable with this idea of predicting precipitation reactions? So you take your cations and anions, you pair them, and you look and see, do I generate an insoluble compound? The insoluble ionic compound is your precipitate. And then from there, once you have your equation written to generate your precipitate, you then balance your equation. Okay, so let's try to apply what we know to another example. So we have silver nitrate reacting with potassium iodide. So first things first, we're going to dissociate all of our soluble ionic compounds, strong acids and strong bases. So we're breaking apart each of our soluble ionic compounds into their component ions. And now what we're going to do is we're going to play a guessing game where we pair each cation with each anion, or as an alternative, you can just swap your cations. So in terms of our list of possible compounds, we have silver plus paired with iodide. Okay, that gives us silver iodide. Gets a solid symbol, it's insoluble. We have potassium plus paired with nitrate. That in turn gives us potassium nitrate. That's aqueous, it's soluble, so that's not very useful to us. We have silver plus and nitrate. That in turn gives us silver nitrate. And then we have potassium plus and iodide when paired. That in turn gives us potassium iodide. So we figured out that only one of our possible products is insoluble, which is silver iodide. So what we're going to do is we're going to write the equation that generates silver iodide as a product. So we have silver nitrate, aqueous, plus potassium iodide, aqueous, leads to silver iodide, solid, and then as a byproduct, we get out potassium nitrate, aqueous. So now that we have our proposed equation, we've checked, and it is in fact balanced. And if we want, we can even show that this is a reasonable precipitation reaction by looking at the net ionic equation. So we have silver plus aqueous plus nitrate, aqueous plus potassium plus aqueous plus iodide, aqueous leads to silver iodide solid plus potassium plus aqueous plus nitrate, aqueous, canceling our spectator ions. That in turn gives us the following net ionic equation, which is silver plus aqueous plus I minus aqueous leads to silver iodide solid. So we predicted the products from this precipitation reaction, and we've written out a balanced total ionic, a balanced equation, and a balanced net ionic equation. Does this example make sense to everyone? Okay, so let's try to apply what we've learned. But one last caveat. And I know this may seem a little obvious, but in order for there to be a precipitation reaction, a precipitate must form. If no precipitate forms, then there's no precipitation reaction. A way that you can tell this, the way you can tell when no reaction is occurring, is if all the ions, elements, and compounds in a net ionic equation cancel, then no reaction has occurred. So let's look at the following example where we mix sodium carbonate and potassium sulfate. Not everything is going to react. So sodium carbonate breaks down into 2 sodium plus aqueous and carbonate, which is CO3 2 minus aqueous. Potassium sulfate breaks down to 2 potassium plus aqueous and SO4 minus aqueous. So testing out and trying to pair our cation and anion, or swapping our cations, we get the following possible formulas. So we have sodium plus aqueous, and whoops, let's not put the state symbol when we're trying to write a formula. So we have sodium plus and SO4 2 minus. We cross our charges, that gives us Na2